Well, thanks again for being here. What? Well, I want to ask a question, but I don't know which one. Probably, since you already voted for something, you have an idea what you voted. So the plan for the rest of the course, there will be, I wouldn't say boring and useless, but some standard academic materials and the labs from now on will be targeted towards new research projects. So I don't know if you were developing any invitation against starting the course, but there was a little mismatch between general goals of the course, policies, and actual activity. So from the title of the course, you were expecting some physical chemistry, and in fact, you got some. Okay. So for how can we approach project we will observe that we try to do some projects from paper. We will try our best to find muscles and essential muscles and do something related to the right, but we cannot do too many relative discoveries in these essential relations. But it would be really nice to have a connection between your right knowledge of the principles and the actual examples, like combustion, explosives, or maybe something less spectacular, more practical, solar cells, or some big things. So for the last part of the course, first month you'll be practicing the whole the problem of principles and last month each of you will choose how you want to solve say reduce complicated problem into a form of one-dimensional potential, which is you may not really know, but it's possible in a lot of cases. And then this code, which is well sort of dynamics for one-dimensional potentials. Do that way, and then you do some mini research, mini presentation as makes sense? And later on, we will formally offer the practice of democracy. We will both not really classical majority against true exam, or prefer to focus on research project. Just like seeds and things. So it will be, as I said earlier, same exam. Not super easy. And it's less stress. So exams, what tasks are you? So the code, since we are devoting 2 months to this code, it's not super easy. Because you code website, code those documents, it's not super easy, it's not 2 lines. It's a little, but it is very good. Just to distribute effort between members of the class, we get a second and analyze how it works, and then in 3 weeks from now, we can present this subject. In previous years, university, the presentation number 3, when class members tried to explain the principles of was the biggest part of the whole performances. So just heads up, bird's eye. In the sense, so not focusing on your view or make connections to this material, other parts. So, whatever labs are remaining before the presentations. So the original plan was to make two endpoints. Just go through lines of code to try to run it and see which line is responsible, which part. So the part. So when you tried to run the script, what have you seen? How does it look? So can you verbally click on something? So anything over hit enter. So you everyone has observed how it works. So right now you do have several versions of the code, and each of them have slightly different potential, but the code is the same. I suggest that you start with the version of the code that has comments, because inherited from previous years, each line was commented, and it will make our assignment easier. And what I also suggest to do is to go to line number 60 and try to uncomment, remove the percent in front of v equals v times 0. So we will go through all details, but there are a couple of systems that you are well aware of, is electron in free space and electron in the box. And if you set up potential energy equals 0, then it will be free space. So you already know everything, how it will work, and you got your understanding of what to expect. So if you make this change, save the code and let it run, you'll see something like this, right? The Mexican sombrero becomes wider and wider and moves from left to the right. What is it? How do you interpret it?
So if it's in free space, doesn't it just like expand out over time? So that's kind of what that's showing.
Yes. So it moves with constant velocity, the center moves with constant velocity, and it expands it changes. Right? So if we would apply this code only for this situation, it would be very silly and boring. But it is kind of universal. It's changing a couple of things and apply it to more and more stuff. So where's your principles of wave packet propagation? Okay. So let's plan to maybe invest time until 6 for the code, and then probably focus on the homework if there will be questions. So let's practice your least favorite activity in the class, browsing through your members. How many ways to predict future you can remember? You should get a Nobel Prize. It's a lot. Maybe a little less, but you can just name them before getting your prize.
Time independent Schrodinger equation, time dependent Schrodinger equation, evolution operator, what's that equation?
It's like 4 and one of them was wrong. You named 4 and one of them was wrong. Well, time independent Schrodinger equation is not for predicting future. It's just one of the general components for anything. But so what Alex named was evolution operator, time dependent Schrodinger equation, and Heisenberg equation of motion. Right?
That's the main choice.
Okay, 4. But let's focus on evolution operator. We spent so long time at the beginning of the course to get through it, and it would be very pity to think that it was just for academic purposes. So we return back to evolution operator. What this code does is not super elegant and efficient. Most practical efforts to solve real-world problem make more tailored, more specific tools for each problem. And here, more for division purposes, we are trying to use something universal. So, how does evolution operator look like? And what to do if you have forgotten it? I read in eyes of some of you that if I have forgotten something, I need to go to Wikipedia. So, what should I write for evolution operator? I don't have it here. It's just your I don't have a cheat sheet. Or generally, what is evolution operator? Maybe I shouldn't print books and just say roughly. What do you remember?
So it is a thing that helps to predict future. It includes Hamiltonian, yes. So it includes Hamiltonian, and it predicts future. So what does it mean, predict future, in a sense of wave function? What is your verbal formula for this? I have no doubts that you all know it. It's just maybe a way to formulate it. Future of an electron, that is always described as a wave function, right? So future means to know wave function of the future. And, future means your time is substantially bigger than 0. And you cannot know the future if you do not know the past. So it's time equal to 0, smaller than 0. So the evolution operator is a thing that converts past into the future.
You multiply by phase accumulation.
I see that you were sitting on the lectures. So phase accumulation, how do I do it? Well, let's first put it like phase accumulation. Correct? So, and what is here? Some people, let me share a way, like if there will be an, I'm not going to do the following. I'm not going to offer an oral example. In some schools, there are frequent oral exams. And if you need to answer something and you do not remember, there is a way to bypass. Like, give evolution operator. You just add a symbol. Put U that goes from 0 to 10. Okay? This is not wrong. It doesn't give the answer, but at least it brings you to the next point of discussion. So what do I do if I have forgotten how to do this phase accumulation? No one knows. If I'm good on the island, and I suddenly decide that I need an evolution operator. Is there any information that we remember, more or less firmly? So since all things are interconnected, one can start from being somewhere apart and then scroll the logical connections. Can we say that we remember time-dependent Schrödinger equation? Yes? Okay, so how do I write it?
dt psi equals negative I over Planck's constant times.
Good. Yeah. Thank you. So, I'm going to do some not rigorous, I would say. If there is an alchemistry, I'm going to do some math. If we, for the time, not for the record, not for the general public. Forget about all differential operators inside the Helmholtz table, and just solve it as a simple differential equation with all constants. D psi over dt, we can migrate dt over multiply both parts by dt and divide both parts by psi. So it will be d psi over psi equals minus over h bar h dt. Right? It's formally right. How do you solve this equation? I always forget who, but I know that 50% of the class is taking differential equations. So you just write integral here and there, right? On the left, it will be integration over psi as abstract variable, and on the right, it will be integration over time. So what is logarithm of d psi over psi? I already disclosed mine. What is the integral of d psi over psi? Okay. And if we want to be very rigorous, we can minus psi naught, right? For the free term. It's not surprises you, doesn't it? Okay. And on the right side, if you just minus I over h bar integral h dt, you just keep it as is. And you know that subtraction of logarithms is just dividing their arguments. So what do you do next if it would be Orson differential equations? Right. So you take exponential of logarithm and exponential in the power of this stuff. Then you get the psi divided by psi naught equals e to the minus I h bar integral h dt. And if you multiply everything by psi naught will be there. So if, and this is the answer for evolution operator. So this psi naught was past, psi, this function of t, is the future. Originally, at the beginning of the class, we were coming up with this equation from some philosophical considerations or model and phase accumulation. But now, with your strengths, you can just formally derive it from Schrödinger equation, right? If you remember Schrödinger equation, you can reproduce evolution operator. So it's question number 1, principles of wave packet propagation. It was a selection of you. Right? Presentations will be brief. There is no guarantee that everyone will have time to show all multitude and strengths of your knowledge, but it's better if you are ready to deliver more than time allows. Let's have some backup slides, yes?
This was the principles of wave propagation.
Wave packet propagation, yes.
Okay.
So the code takes initial wave function. We set up initial wave function at time 0, and then apply the evolution operator to get wave function at some later time. There is a little technical detail. I'll keep it on the board for briefly. In order to avoid numerical error, the propagation is made by infinitesimal, which means small time. So instead of integral, it's just Hamiltonian times increment of time. And we are propagating forward not by long time period, but very short time increment. So if we believe this that this is an appropriate way to predict future, then we need to loop this procedure. So we need to make redefine t equals t plus delta t, psi of t equals psi of t plus delta t, and then we need to repeat this procedure, right? And then our code will go through from time equals 0 to time equals delta t, then 2 delta t, then 3 delta t, and it will propagate forward in time. So the main principle is loop through infinitesimal increment. So there are two aspects of dealing with it. First, where this looping is in the code, which we can glance through and find immediately. And another aspect, we are departing from abstract mathematical symbols. We are recognizing that each operators are either differential operator, or if we are in finite differences, it is like derivatives in finite differences. So Hamiltonian means like potential plus kinetic energy, and all these things are operators that need to be defined. So there are two things: where this stuff is in the code, where the loop is, and second, how the Hamiltonian is defined. So the Hamiltonian, which was the choice of Kevin, by now I didn't have time to like approve distribution. Maybe later on we will make sure that everyone has even share. But by now it is Kevin's choice, Hamiltonian. But we cannot go directly to Hamiltonian for the following reason. Hamiltonian does include kinetic energy, and kinetic energy depends on momentum. Momentum is more basic than kinetic energy and Hamiltonian, and first we need to go over momentum and find a way how to define it. But before we go to definition of operators, let's scroll through and find lines of the code that will correspond to this loop. Which command in the script sets up a loop, a cycle? Okay, so we are going forward and looking for loop. We are looking for command 4. No, this is not, because this is not, this is not. Scroll, scroll, scroll. Scroll. We are very close. Okay, so line 164, if you are using WP3 AVP comments, the version with comments. So the loop variable scrolls through several time steps, which, as you can guess, is defined by a number of time steps that we need to come through and tau. Okay, and line 172 is implementation of this equation. So this is referred to as variable psi2. This is also referred to as variable psi2. And it is not variable, it's just it's a vector of, for the wave function, which is defined at several positions. And the evolution operator is defined by this G tau 2. And if you scroll further down, you'll see that this loop ends, and the script is mandated to go over this loop again and again. Any objections or protests? Okay, so let me make a little comment irrelevant to your presentations, just for general understanding of the code. So we are propagating forward in time. At each point of time, we recompute wave function, and as soon as we know wave function at a given point of time, we can find some observables, like expectation values of whatever position, momentum, or maybe something more complicated. So it is what this code will be doing. And in addition, at each moment of time, the wave function can be converted into a probability distribution that can be plotted as a function of position and time. If you scroll through stuff that code generates, you'll see that one of the things coming at the bottom, it looks like Gaussian shape at the beginning, another axis is time, and it gets lower and wider. So it's probability, and the movie that you see is also probability distribution as time goes by. So although we are predicting and computing wave function, we are displaying probability. Why? Why there is a optimal decision to show visualized probability distribution instead of wave function?
Isn't that like observable?
Yes, and practically, what is wrong with wave function? What is not comfortable?
It's imaginary.
Yes, and our vision is real. Right? So if you need to plot wave function, we need to have it either to have imaginary vision, or we need to plot simultaneously real and imaginary part, which we did once in the past. And immediately next line, here is a prop2, psi2 star, conjugated psi. So this is a probability distribution at given point of time. Okay, we are done with principles of wave packet propagation. There are some additional things, but it will be too much for now. Momentum operator. This is really challenging stuff. I need to erase things from this board and start over. You don't need this. I have your permission to erase it. What is sketched here? What is your opinion? Yes, but why I decided to avoid drawing a continuous line and put just ugly sticks up? Can computer digest continuous lines in general? No. So any function is just a set of discrete values. One needs to some values of x and some values of y, right? So if we want to define the function by values as certain arguments and certain values of position, we need to define the grid, discrete space. Continuous positions are represented only by selected points in space, which start from initial, ends with final. We have as many as n capital, and maybe we will find out, maybe the code use something like nx and n position, we'll check it out. And each grid points are offset by step in position, delta x. So offset of position offset between grid points. So our wave function, which we will call the psi2, it will be a column vector of these values, psi naught, psi of delta x, psi of 2 delta x, psi of 3 delta x, as many as we need, psi of n capital minus 1 delta x, psi of n capital times delta x. Make sense? So it's not a big discovery, it's a standard thing in, if you do computation, but it's better to verbalize it and have it as a part of your presentations, because it's so easy to skip important things and then lose connections. I'm going to ask a question, but I'm not expecting an answer. Just giving you a seed of thought. You are absorbing an idea that wave function is equivalent to column vector of large dimension, and an operator is equivalent to a matrix of this many points squared, right? So right now the question is how the matrix representing momentum operator will look like. If you have an idea, try it. If you don't, it's fine. Just try to think. This is a main challenge. It would be our main challenge if we would decide to design this code from the beginning. So how to implement momentum operator, because the rest can be rolled over. Everything can be for kinetic operator. Just take a square, multiply it by itself, and so this is a challenge. How do we start to address it? Probably I would do the thing that you hate and scroll through my memory for definition of momentum operator. P equals what?
Negative IHDEX.
Excellent. So psi is a column vector with n elements. We need to design a matrix of n times n, which will be equivalent to the differential operator. So we need to define derivative in finite differences. Even if it is not your subject to present, please do not think that it's for him, for her. I can sleep. But we will need this part of information for all following steps. Just friendly reminder. So, derivative in finite differences. What is the definition of derivative? I'm not challenging your knowledge. 100% sure that you know. It's just I'm challenging your ability to verbalize it in a short sentence. Okay, relative change of a function. Slow, yes.
Change of position at a very small time.
Or if our independent variable is position, then change of a function for very small change of position. So change of a function. It's like election slogan of the previous president, change. So psi of x plus delta x, that's it, minus psi of x divided by delta x in the limit that delta x goes to 0. What do you think? Would you approve? Anyone develops protests? No? Okay, so from now on it is definition of variable approved by majority. Can we implement this definition in the space of these discrete values of the wave function? Mute. So, what we can try to is to assume that we already got the momentum operator that has acted on our wave function. So instead of deriving operator, I'm going to write something that will give us result of application of the momentum operator, derivative operator. I don't know how to start it logically, but I'll start writing and maybe you'll find better way to verbalize it. So, at grid point 0, it will be value of wave function at next grid point, 0 plus delta x, minus value of a wave function at this point, 0. Divided by delta x. At grid point number 1, it will be subsequent, next one, psi of 2 delta x minus psi of delta x divided by delta x. At grid point number 2, it will be psi of 3 delta x minus psi of 2 delta x divided by delta x. What am I doing? How to verbalize it? Psi of let's say k plus 1 multiplied by delta x minus psi of k times delta x divided by delta x. Next, minus previous. Yes, please.
Aren't you just grabbing the first one?
Huh?
Oh, you asked what you're
Okay. Next, minus previous with this height. So we are computing the offsets of the previous minus next minus previous. This much. This much. Here it will be not much. Here it will be negative. Here it will be negative. Okay, right? So the change of the wave function in respect to the step along x. Well, in some sense it is slow. I just do not want to use this word because if psi is complex, then it will be complex. But we are practicing in order to implement momentum operator. We are practicing finite differences. So we subtract values of function at nearest neighbors and store it at the spots corresponding to the appropriate grid points. Any objections about this procedure? Like, would you agree that this procedure in discrete space would be implementation of the definition of derivative? Yes?
So is it just a summation of all the offsets, or what?
No, it's not summation. Those are, this is a vector, multidimensional vector of so many elements. And each element of this vector is this subtraction. Okay? So result of applying momentum operator to wave function will have the same nature as wave function. If our wave function was a column vector of so many values, then result of application of momentum operator will be again column vector of so many values. Okay? We are very, very close. Now, let me check if the it is in focus. So now the main part of the computational implementation of momentum operator. So here I will write a vector for wave function psi. So I will repeat just when I need to calm down, I just repeat some words right. I will write it once again. Psi, psi delta x, psi 2 delta x, psi 3 delta x. Now, I do want to design such metrics which will help me to practice row by column procedure. And by applying this unknown matrix to this set of numbers stored in the column, I will get this set of numbers.
If you just put all those grid points on the diagonal, and then make the rest of the number 0 in the matrix?
No, the matrix will be not diagonal. But the good news are that here, let's start from this one, from the first element. So in order to obtain the first element of the result, we need just two first element of the, how to say, reactant, precursor, if you speak chemical language, mathematical reactant. We need to use the first one with minus sign and next one with plus sign. And all constants will be put out of brackets. So this element, I can already break it onto cells. So in order to obtain this element from here, we put zeros comes with -1. And the first comes with +1. And the rest elements do not contribute to here. So we put zeros. Make sense? This is one of the hardest part. Do not worry if it doesn't go smoothly. Just slowly. If you practice row by column, if you multiply this row by this column, -1 times psi 0 will give this one, and +1 times psi of delta x will give this one. And there are no others contributors. Now, for the element here, do we have psi defined at 0? No, so we put 0 here. Do we have psi defined at 1 delta x? With which sign? Negative. -1. Do we have psi defined at 2 delta x? With which sign? Do we have psi defined at 3 delta x? Okay. Let's repeat further. I don't want to distort you from your comfort, but next year probably it will be good practice to call everyone one by one and draw it. Keep sitting, don't become nervous. So, do we have for this term? Do we have contribution from psi 0? Do we have contribution from psi at 1 delta x? Do we have contribution from psi at 2 delta x? With which sign? Very good. Do we have contribution from psi at 3 delta x? Which sign? And then zeros. And then it's enough. We do not need to progress further because we catch the pattern. So on the main diagonal, it will be -1, -1, -1. On the upper subdiagonal, it will be +1, +1, +1. Right? This is the main principle of defining momentum operator in discrete computerized space. Yes?
What happens when you get to the bottom right corner?
We apply periodic boundary conditions. I didn't answer anything, I just used smart word. So we put +1 here and -1 on the diagonal. So this code becomes possible in two cases. You know that we do not have computers with infinite number of grid points. We always need to have finite number. And our space is infinite. The question is very good. So how do we describe infinite space with finite size computer memory? There are two ways. Either to assume that there are walls of the box, and at some point it will reflect, and then we just put zeros at the edges because there is no momentum if it hits the box. Or we implement so-called periodic boundary condition concept, which is one of another challenging concepts. That's when you present a little later. Please switch on your imagination and assume that I'm ramping, and I smash into the wall. You can imagine it, right? It's very satisfying. And instead of smashing into the wall, suddenly I disappear and reappear from the door and entering the room from other side. And then running again, smashing into the wall, and instead of like really smashing, reappearing from the door. Imagine. So it is periodic boundary condition. So instead of reflecting, I just reappear from other side. Therefore, I put +1 here. Okay? Good. So there are some additional technical details. Like this matrix is very convincing for common sense, but it is not symmetric. It is a little better if we define this plus and minus not along the main diagonal, but along two sub-diagonals. And actually, did you ever heard about names Runge Kutter? No, okay. The derivative here has limit, delta x goes to 0. But if you do practical applied math, there will be always an error between abstract derivative and finite differences derivative. There is a way to take into account additional terms that you implement psi of x minus delta x, psi of x minus 2 delta x. They will contribute less and less. They will be vanishing. It's like Taylor series. But they will make derivative more exact, mathematical. So in realistic implementation of momentum, there are some additional tricks, which we do not care right now. This equation is sufficient. If we literally type it in, the code will work. It will give a little less precision, but it is a correct approach. So we should finish the code and probably switch to homeworks, which you may be interested in, right? So let's quickly find where this momentum operator is defined, and it will be enough of coding for today. So one definition of momentum operator is in line 108. This will not look like what we were discussing, but if we plot this P sub Px, it will look similar to what we discussed. It is defined through more complicated procedure. And since one of the features of a true scientist, ideal scientist, I wouldn't say true or untrue, is an attempt to find his or her own errors rather than let others to find them. So to be critical and try to look back and identify if anything was not trustable enough and try to improve precision. It's not sufficient, like anyone who finds error doesn't mean automatically becomes successful scientist, but it is a good thing. And driven by this idea, we will have alternative ways to predict future, like alternative futures. They will use similar methods with little technical differences. And we will see that at short time, for simple systems, they will develop identical predictions. But as long as we go more further and further forward in future, they will start slightly diverge. So there will be several definitions of P operator. There will be another one. So this is line 108. Another one is in line 126. So we are already at the limit of our abilities to absorb new information. So how do we plot, how do we visualize matrices? Okay, so I was plotting the px object, and if you type in size px, you see it is a matrix. It has a dimension 200 by 200. Wave function is 200 elements, and matrix is 100 by 200. If you try to plot real part, it comes some strange, almost constant value. If you try to plot imaginary part, we see things which are large near the main diagonal, and then they are smaller and decreasing on the subdiagonals. So this is implementation of the stuff that we have behind the screen. Okay? So the main diagonal is whatever we predicted it to be -1. Here it is something different, and then it changes sign. And in order to make definition of derivative or momentum operator more precise, it alternates sign and decreases very quickly. And this stuff at the edges is added in order to answer a question by Alex, in order for me to smash into the wall, in order to implement periodic boundary conditions. Right? Enough? Any questions from Bill? Because you signed up for this subject. Huh? Okay. Okay. Good. So let's take a breath. I will erase the writings on the screen. Let's see. And then I will make a circle and develop an interview. Which problems of the homework induce most of the questions?
I had the 2 for the position board, where it's like, does that say, that's the square root of the 8 font? Because here, look at the position. I have a 2 MW. Instead of here, it just says the MW. So I don't know if that's. That kind of made, I mean, I didn't see it. I don't know what you This is just for
You don't answer all.
Yes.
2, 3, 6.
I'm not sure if I will attend conferences, although I never read it.
It's 2 week kind of covered in class, right? A little bit.
It was a
Slightly.
it was extra credit of previous school.
Yeah.
It was not
You have to like integrate.
Yes.
Okay.
And one of the colleagues, one of the colleagues of this table, says we have that's where it gets up. It's a large. I think I will also start from 42.
Start.
Well, first is 2, is not really changing. First, it was like, this one.
This like that's the X, and then your terms. This is like your 1. Then 1 equals the interval, and then that's your wave function. That's your operator. Yeah, and then that's your wave function. See, that's what I don't know. This is what your the psi star psi. That's I need to read. I don't know how to set that out. So I don't know if you use the square root of h at over w. Yeah. Or what you do. Because this you just a and I wonder if it's the same.
Really?
Yeah.
You're comfortable using. There are different.
Should I have to talk?
Sounds good. Sounds good. Alex is always
That's from, that's Yeah.
Buffalo. Yep.
Huh? What is it?
That's what I just said. I just said Buffalo.
I don't know if she heard you.
Oh,
I did not.
you heard that?
Yeah.
Yeah.
And then he turns around and just
Number 6.
So, let's go to
Extra question. 3.
as I go through.
16,
Oh, this is actually.
Yeah.
Because I got my
This was like this was from last time.
Because you know, it's,
The second one? Second one?
I think it's like, cause it's like, create your sine duplex, something like that.
yeah, I mean, say, from, something,
I did get non-zero.
You're trying to
I got
zero.
zero.
Yeah, yeah, it's just-
It was non-zero, or it's like the opposite.
okay. Just makes sense.
So then it would be.
Just.
And then the other one is just the opposite. And then,
Then they just complete this. Oh, yeah. So. I got it.
Thanks. Give you class.
we discussed this in my.
Oh.
Yeah, I think so.
I haven't finished plans yet, but we.
Oh.
But I know I have.
I mentioned it
Me.
to Rachel. I guess that means more than Rachel. I don't know if you agree with that.
Never actually seen all these versions.
Ever seen a bullet?
She should want to give away some, but she could put it in one thread.
So, was it everyone agreed that 2A is the bottleneck to go forward? Or some of you go through? So the little comment on 2A would be, you wouldn't vote against it. Okay, good.
I skipped one, that was just like, I would put that.
So when we finding a matrix element, we just plug in the x instead of operator, and our phi 1 star, or if you will, bra of state 1, and phi 1 without star, or if you will, cat of state 1, and then integrate. So it will be integral 1 over L sine x squared by x over L times x dx. So the sine square function has maximum worth on the halfway, and it will parse. So here the resulting function is 0. Here is 0 again. So product of x times sine pi x over L will be maximum near this L over 2. And if you integrate it carefully and take into account of normalization, you should get L over 2. It's just expectation value to find electron, most probable place where electron can be found, if it is residing in the first state, the ground state will be the middle of the box. I'm not doing the math, but I will be checking and grading. I'm checking it. I'm checking. This integral is doable, but and the same for 2x 2. You do the same practice, and when you find that it is L over 2, it's the right answer. The thing for grading you just how you grade it. But the off-diagonal matrix elements of position 1, x, 2. This is a true mathematical challenge, and I'm willing to give some comments to help everyone to go through. If you have successfully completed this part, just go forward with other assignments, with other tasks. But if not, let's discuss it. So we are practicing again integral 1 square root of L sine pi x over L times x times square root of L sine 2 pi x over L dx. So there is nothing physical, there is nothing chemistry, it is pure math, right? But we need to get through it. There are 3 ideas in order to take this integral. So first, convert product into sum. Second, upon we get a sum, treat it as there will be 2 independent integrals, just to save space and do them one by one. 2 integrals. And third will be integration by parts. It's not any, there's nothing new for you. You know integration by parts. Integral of u dv equals what? right? So if we practice 3 of these steps, we should get something like 2/9 square root of L, or 1/square root of L. I don't remember it from the top of the head, but I'll try to go over the steps. We need to jump to get it back.
What did I do? Oh, that's. Yep.
Yes.
No, it's a box with a length of 2 nanometers. Would there be any potential energy
Huh?
for number 3? With the box being so small, would it just be no potential energy?
Inside. Just recall the, so for number 1, recall the energy of the first state in the box, which will be inversely proportional to size of the box, and it will be like h per square, pi square stuff. And you need to, if you set up energy equals 2 eV, then you solve for L by plugging in the values of constants. Okay? So I don't remember it from the top of the head, but it will be, we already did this conversion in the code for density of states. So some factors were there, or it was a way to avoid factors through this atomic system of units. And the size will be, for 2 electron volts, it will be of the order of like 1 nanometer. But I don't remember exactly. So there is summation of 2 signs. And integrals of products are always challenging. It's much easier to kind of to process summations. So is there a way to convert this product into summation? There should be 3 trigonometric identities which we can and I don't remember this conversion identities, when I'm in doubts, it's better to rederive them through Euler equation. So if you do not trust me, which is a normal thing, just rederive with Euler or look in Wikipedia. If I'm lying at this equation, the rest will be garbage. Well, maybe only the ideas will be more or less useful. But if this conversion is correct, then product of two signs, this will be alpha, this will be beta, then we will have 1/2 minus cosine. So alpha plus beta will be 3 pi x over L. And alpha minus beta will be cosine of minus pi x over L. Well, cosine is a symmetric function, so it's nothing wrong to replace sine by cosine. So if this was correct, then our 1x2 matrix element will be rewritten as 1 over L from normalization. Then we will have brackets, two terms, two integrals. First integral will be also 1/2 outer brackets. So first will be this minus sine cosine pi x over L times x dx plus second integral from 0 to L capital cosine pi x over L times x dx. There is nothing wrong in looking online for Wikipedia or looking in tables of integrals. If you know how to use them, or if you, in addition to MATLAB, there is another very popular tool for mathematical computations, so-called Mathematica. It solves radicals. It does analytical calculations. So I'm trying to instruct how to do it by pen and paper, but if you have alternative ways, it's absolutely acceptable. We need the answer and analysis of the answer. So there are two integrals. One that depends on pi x, we can call it I1 because it's, and I3 because there is a cosine 3 pi x. Typically, the most very simple integrals that we take in definitions, it's trigonometric or several trigonometric functions, or only polynomial functions. But here is the little challenge that we have a product of polynomial and trigonometry. So we do not know what to submerge under sign of differential. So I will try to take this I1 integral and see what happens. So I1 integral cosine pi x over L times x dx. So we already done with first and second. Now we are doing the third part. So if we do not know how to take integral, and we do not have ideas, we just try several rules that we know. And one of the rules is this integral by part. So we need to identify what will be u, what will be v in this expression. But if x is u, then what will be the v? You're right, I agree with you.
Oh,
So what will be the v?
the integral of cosine pi. So like,
So we may want to identify this combination of cosine dx
that's dp.
as dv, right? So we are going to submerge cosine under the sign of differentiation. So what is the integral of cosine? Positive or negative? Positive. Okay, so it will be d sine pi x over L. And what should we do to the constants? We probably need to flip this stuff. So put L over pi at front, right? Because when we will be taking differential, the pi over L will come up front and we need to compensate it. So, integral. Are you fine with this expression? Is the logic acceptable? So we hope that we will be able to practice integration by parts. And we did submerge the cosine under the differentiation sign. Now we have x is considered as u and d sine considered as dv. Now let's practice u times v minus integral v du. Just practice this rule. So we keep the constant L capital over pi out of brackets. Then we have u times v. So x times sine pi x over L capital explored at limits from 0 to L capital. Minus integral v du. So our v is sine pi x divided by L, and our u is x, gx. Close the bracket from 0 to L. So what will be the sign of pi x over L if x equals L? It will be sine of pi, right? If x equals L, we have L divided by L, 1. What is sine of pi?
0.
0. And what will be this expression when x equals 0?
0.
So you don't have this term. L divided by pi, we inherit minus sign, and then what is the integral of sine? Dx. So it will be negative cosine. So we get one more minus, minus 1, minus 1, which will likely cancel each other. We have L over pi from our conversion to this u and v variables, and we are going to have another L over pi from this integral. So we are getting L over pi squared times cosine pi explored in the limits from 0 to L capital. I'm not the champion in smart use of space, therefore we will go up from here. I1 equals L squared pi squared. What is value of cosine of 0? 1. Minus 1 at lower limit. What is the value of cosine of 1? If you plug in here, no, cosine of pi. Negative 1. So, minus 1 will be minus 1. Just kidding, minus 2. Minus 2 L squared divided by pi squared. Okay? And then you process the integral I3 by the same protocol. The difference will be only the factor up front. So everywhere where we had L over pi, we will have L over 3 pi. Right? Everywhere where we had L squared over pi squared, we will have L squared over 9 pi squared. And the sign in front of this integral is negative, right? So if we, if you want to process the I3 integral, it should be same stuff as here with opposite sign. So plus, you have 2, you have L squared divided by pi squared. But in addition, we inherit the factor 9 in the denominator. And if we add together I1, how was it? I3 plus I1, it will be 2/9 L squared over pi minus factor 2 will be like 18th divided by 9 L squared over pi, which will be like 16 L squared over pi. But double check. I like making errors, not intentionally.
You mean that's that?
The answer for the overall stuff will be will be 1 over 2L times use I3 plus I1, which will be 1 over 2L times 16 L squared over pi squared.
9 pi squared.
Over 9 pi squared, yes, correct, thank you so much. Alex plus 1. And then we can cancel 2 and 16 here, getting 8. And we can cancel L here and 2 there. So we will get 8L over 9 pi squared. Okay? Similar to your independent practices? Haha, good. I'm so happy to be supported by someone. Because you see through this chain, there are so many chances to make mistake. And while grading, I'll try to be generous, understanding that it is not an easy thing to do. So we will run to the next problem, but do you see any value? What is the use, what is the benefit of this matrix element for real life? If you accept the hypothesis that the course is not a mean to torture young minds. Any connection to real life? Well, of course, in the question number 3, we will find dynamics of expectation value of the X operator. But this can be considered as torture of students. Is there anything more general, useful? Why? What is your opinion? About the off-diagonal matrix element for the particle in the box. Anyone? It's no way for grade. It's just bird's glance onto the things. What is dipole? Dipole, yes. It's magnet. Well, there is no magnetic. There is magnetic dipole. There is no magnetic monopole. But electric dipole. If there are positive and negative charge nearby, if there is a positive
arrow pointing partial charges.
Correct. So if there are anion and cation or positive and negative charge nearby, and they have equal
Your call will be
charge,
disconnected.
and they are offset by distance r, or we can tell x, then the dipole will be equal charge times their distance. This is really important because dipole gives a very specific pattern of electric field. Like if you draw electric field sourcing from single charge, it will look like a hedgehog, right? Field will come into all directions. But if you look onto field of the dipole, it will be force lines starting at plus and ending at minus. You saw these pictures probably in some textbooks, right? And if you have polar solvents, they have dipole at each molecule, right? One thing. Another thing, if you apply voltage and electric field, your dipoles will rotate along the field, same as compass, right? So the energy of interaction between electric field and your polar molecules will be just electric field times dipole, which can be vector. And this is not the end of the story. Just relax a little. I'm trying to entertain you, as much as scientists can entertain other scientists. If your molecule is being irradiated by light, if it is able to absorb light, if it does have ability to absorb and emit light and has spectrum, you know that sometimes people draw spectrum, wavelengths, absorbance, and near the visible light some spikes, right? So intensity of ability of molecule to absorb light at certain frequency is proportional to transitional transition dipole squared. And since dipole is just depending on electron's charge, we can put charge out of brackets and tell that it is transition between quantum state I, quantum state J, bracket square. So taking matrix elements of the position operator is critically important. It's like 50% or maybe a little less, 40% of scientific efforts in theoretical spectroscopy in trying to compute ability of molecules to absorb and emit light. So when molecules absorb and emit light, we need to compute matrix elements like this. Or if it is not molecules but particles in the box, if those are quantum dots or quantum nanowires,